Hey guys, Ms. Marusik here, and in this video we're going to continue our discussion about how to illustrate the dissolving process. Just now we're going to look at it on a larger scale. We're going to also in this video talk about dissolving equations as well as how can we tell if a solution is an electrolyte or not. So to start us off here, you notice that we have three different substances that what we want to do is we want to illustrate what a beaker of these substances might look like once they've been dissolved in water. So whereas in the last video we showed the actual intermolecular forces that are forming, here I just kind of want to have a grand scale of, is the dissolving taking place? Are we forming ions? Or is that substance staying together? So to start us off here, I need to first figure out for each of these whether or not they're soluble in water. And so I'm going to start off here with my magnesium chlorate. I'm going to first identify that as being ionic or covalent. I see that it's a metal polyion combination, so I know that it's ionic. And so I would want to use my ionic rules to figure out its solubility. Now, this is not one that fits the group 1 ammonium or nitrate rule that AP would expect us to know. So to figure this one out, I actually do need to consult the solubility table. And when I do that, I would go through and I say, well, I already checked group 1 ammonium and nitrate, but I do see here chlorate. And this says that all chlorate compounds are soluble and that there's no exceptions to that rule. So this one would be soluble. Now, once I see that, I am going to need to get myself a formula for this substance. Magnesium is +2. Chloride is ClO3 -1. And so I'm going to need 2 of those chlorates for every one of the magnesium. Now, as we saw in our earlier video, ionic compounds tend to separate into their ions when they dissolve. That water ends up surrounding our ions. And so what's going to happen here is that this substance will undergo a process called dissociation. The magnesium chlorate will dissociate into its ions. Now, when I'm trying to show this on a bigger scale, I wouldn't worry so much about showing how the water is interacting with these ions, but I would want to show that the water split up the ions. And so what I'm going to do in this solution is I'm going to draw me some magnesium ions, and I'm going to draw me some chlorate ions. And because I have 2 chlorates for every 1 magnesium, I'm going to actually address that ratio in here. So notice I am doing a 2-to-1 ratio between those ions. Now, could you draw more of those ions? Sure. You would just need to maintain that ratio. So if you wanted to draw 2 magnesiums, I would need to draw 4 chlorates. If I drew 3 magnesiums, I would need to draw 6 of the chlorates. But I do want to show that those ions are separated once they've been dissolved in water. So for our next substance here, we have silver chloride. So again, I would first want to ask myself, is it ionic or covalent? What rule would I use? I see I have a metal, non-metal combination, so that is ionic. And so then I would want to use my solubility rules to figure out if it's soluble. Well, it doesn't fit the group 1 ammonium or nitrate rule, so I'm going to consult my solubility chart here, and I see that I have not a group 1, not an ammonium, not a nitrate, acetate, chloride, or perchlorate, but I do have a chloride ion in there. Now, there's some exceptions to chloride. Not all chlorides are soluble. Some exceptions include silver, mercury 1, and lead. And I notice that in here, lo and behold, I do have the silver present. And so therefore, this would be insoluble. It would not dissolve in the water. What that means is it's going to make a solid precipitate. If I was doing this in a reaction, as far as its state is concerned, I would want to put an S with it for a solid. Now, I still am going to go ahead and figure out my formula. Silver is +1. Chloride is -1, so those balance out. But if I put this into water, because it doesn't dissolve, I'm not going to see this split up into ions. A solid precipitate would because of gravity, get pulled eventually to the bottom of this solution and end up sitting down here. So what I'm going to do is I'm going to draw me a little pile of solid down here, and I'm going to label this AgCl. So that's where my solid precipitate would be residing. All right, our last one here says phosphorus trichloride in water. First off, I'm going to ask myself if it's ionic or covalent. Phosphorus and trichloride are both nonmetals, and so that is going to be a covalent. Hence why we see the prefix of tri with the chlorine in here. Now, to figure out if a covalent is soluble, I'm going to have to think about the polarity of phosphorus trichloride. So this is where it really does help to draw it out. Now, phosphorus trichloride, I would have my phosphorus with an unshared electron pair, and it would be bonded to 3 chlorines. I'm not going to put all the dots on chlorine. Obviously, this would each have some peripheral electrons to them, but I can see just from looking at the central atom that this is going to be polar. And so in being polar, it would dissolve in polar water, like dissolves like. And so therefore this one would be soluble. Okay, so I'm going to go ahead and put my PCl3 here. However, covalents do something interesting. Rather than splitting up into ions, remember this is where the IMFs between the partially positive and partially negative ends would form and attract. So this PCl3 is actually going to stick together when it's in the water. It's just going to be attracted to the water's poles. So to show that in here, I'm just going to leave the PCl3 together, and I'm going to put, hey, I've got some PCl3, some PCl3, some PCl3. This does not dissociate into ions. It is dissolved, so it's in the solution, but it doesn't split into those ions. It sticks together because it's covalent. All right, so this is one way on a grand scale we could represent what solutions might look like. Another way on a grand scale that we could represent solutions is by using what is called a dissolving equation. It says here if an ionic compound is dissolved, we can show the ions that the substance breaks into. Very similar to what we did up here, it's just now I'm going to be showing it in an equation format. It says the ions must be shown with charges or your equation is wrong. So be very careful on that. That's a common mistake that people make. If you don't put the charges, then technically those ions, you're showing them as a neutral compound, and that's totally different. It says here if a covalent compound is dissolved, we can show the substance becoming AQ, but we cannot break the substance into ions. Again, we addressed that here where we said the covalent, even though it's dissolving, is going to stick together. And then last but not least down here, it says if the substance does not dissolve in water, then we cannot show an equation for the dissolving. So let's practice with this on the next page. It gives us a chart here with some various substances, and it wants us to write dissolving equations for each of them. If it doesn't dissolve, then we're not going to write an equation. So we're going to do a couple of these together, and then I'm going to let you try some out. So let's look at the first one here. The first one says that I have sodium phosphate. And so the first thing I would do is ask myself, is this ionic or covalent? And I see I have a metal polyion, so this is ionic. Next, I would want to ask myself, is this soluble in water or not? And to do that, the first thing I would do is ask myself, well, can I use those AP rules that I need to memorize? Do I have a group 1 ammonium or nitrate here? And if I look on my periodic table, I will see that sodium is indeed in group 1. And so I don't even have to check the rest of this. I know it's going to be soluble. So being a soluble ionic, that will mean it will split into ions. And so what I'm going to do is I'm going to first write my formula for sodium phosphate. I know sodium is +1. Phosphate is PO4 -3. And so to cancel out those charges, I am going to need 3 of the sodiums. Now you notice here on my official compound, I didn't show charges. That is proper notation to show our compound as being neutral. Now something else we can do on a dissolving equation for an ionic is that we know most ionics, before I put them into water, would be in the solid state at room conditions. Remember, they have bonds versus forces that are holding them together. And so those being very strong, we can predict high melting and boiling points. So I'm going to go ahead and put solid there for the state. I'm then going to put a one-way arrow, And I'm going to show what this dissolves into, what kind of ions form, since it's ionic, when it dissolves in water. I would break up into 3 sodium ions. And I'm going to show, because it's an ion, its charge. And now I'm going to put that it's AQ because it's dissolved. And then I'm also going to put that I have my phosphate. Again, it's an ion, so I want to show it with its charge. And again, I'm going to put the AQ state. Now, College Board would not take off on the AP test if you did not include the state. That's really not that big of a deal. But what they would take off on is if you did not show those charges. Writing sodium with no charge versus sodium with a charge are very, very different. So we have to be careful there on that designation. All right, let's look at our next one here. I have magnesium dichromate. Again, I'm going to ask myself, is it ionic or covalent? I have a metal polyion, so this is ionic. Next, I want to figure out if it's soluble or not. So since it's ionic, I would want to use my solubility rules. It's not a group 1 ammonium or nitrate, so I'm going to go ahead and consult my chart here. Now, this is one where if I start working through these rules, I don't have a group 1, I don't have an ammonium, I don't have a nitrate, acetate, chlorate, or perchlorate. I don't have a chloride, bromide, or iodide. I don't have a fluorine. I don't have sulfate. So then I come down here to this bottom half of the chart. I don't have a hydroxide. So basically what that means is that everything else is insoluble. It would not dissolve. It would make a solid precipitate. There are exceptions of group 1 and ammonium, but hopefully we would have checked the group 1 or ammonium way back up here. So for this one, it is insoluble. Now that's totally awesome because that means I don't have a dissolving equation. So I get to just scratch that out. Makes that easy, right? All right, next one, phosphorus trifluoride. Well, I see a prefix in there with a non-metal combination. And I'm like, that sounds like that guy is covalent, which it is. Now, next I would need to decide if it's soluble or not. For this one, because it's covalent, I would need to think about like dissolves like. I would need to think about the polarity. And very similar to the phosphorus trichloride we saw just a few minutes ago, phosphorus trifluoride would look something like so. And then, of course, our fluorines would have dots surrounding them. So when I'm looking at this structure, I notice that it is indeed polar. It is unsymmetrical because of the unshared electron pair causing an overall dipole moment here. And so what that means is that this would be soluble. Again, if it's polar, it will dissolve in polar water. However, it's covalent, so it's not going to split into ions. And so therefore, what I would do is I would say, hey, I have my phosphorus trifluoride, and I don't know what the state of it would be at room conditions, but what I do know is that once it dissolves, it would stick together and be aqueous. Now, I know that looks kind of dumb. You're like, she just rewrote the same thing and just showed it became aqueous. Yep, that's what I did. It dissolved, it became aqueous, but it didn't split into ions. As silly as that looks, that would be how you would do your dissolving equation there. All right, one more we're going to do together, calcium hydroxide. Again, I would ask myself, is it ionic or covalent? I see I have a metal polyion combination there. Be careful, hydroxide is a polyion, even though it has an "ide" ending. So being ionic, I would want to consult my solubility rules. I don't have a group 1 ammonium or nitrate, so I'm going to go ahead and consult my chart. I don't have a group 1, I don't have ammonium, I don't have nitrate, acetate, chloride, or perchlorate, I don't have chloride, bromide, or iodide, I don't have fluorine, I don't have sulfate. However, I do have a hydroxide. Now it says here that hydroxides tend to be insoluble unless it's a group 1 ammonium, calcium, strontium, or barium. And I'm like, I see my calcium there. So what that means is that even though most hydroxides are insoluble, calcium hydroxide is soluble. It would be AQ. So in being soluble, that means I can write a dissolving equation for it. And because it's ionic, it would dissolve and split into ions. It would dissociate into ions. So I'm going to have calcium. I know calcium is +2. Hydroxide is -1. By the way, I'm going to show you kind of a trick you could use here with this before I put the hydroxide over here. Sometimes it helps to go ahead and do the product side first. Like I know that calcium is +2, and that's going to be aqueous. I know that hydroxide is -1. That's going to be aqueous. I see those charges don't cancel out, so I would need 2 of the hydroxides. So then I can come back to this original side and say, hey, for every 1 calcium, I would have 2 hydroxides. Don't forget to put your parentheses around that OH. And originally it was ionic, and so I'm going to assume that it was solid to begin with. So sometimes it helps to almost kind of do these backwards because then you don't have to worry about figuring out those charges on the compound. You already got your charges and you can cancel them out before you write your compound. All right, here's what I want you to do. I want you to pause the video for a moment and see if you can try out these next 3 examples, and we'll check them here in just a moment. So go ahead, pause that video, try them out. All right, I'm going to assume that you did. I'm going to go ahead and put my answers up here. And so here's what I got for those last 3 examples there. Barium acetate is ionic insoluble, so it does split up into ions. Strontium sulfate is insoluble. If you look at your solubility rules, on the sulfate rule, strontium is one of the exceptions, which is why it is not soluble. So I didn't have to do an equation for it. Ammonium carbonate has ammonium in it, and as we know, all ammonium compounds are soluble, and so therefore that one would dissolve. All right, let's go ahead and look at our next section that talks about how can we identify an electrolyte solution. Now, an electrolyte solution is one that conducts electricity, and so in order for that to happen, we must have charged particles that can move. So for a solution, that means we must have dissolved ions happening in the solution. I can't just have a covalent substance in there. I have to have those dissolved separated ions to do this. Now, there's other substances that do conduct electricity. For example, metals conduct electricity, but we wouldn't call them an electrolyte because they're not a solution. So we kind of reserve that term strictly for solutions, that term electrolyte. We do have some different categories here. The first of those is what is called a strong electrolyte. These are solutions that conduct electricity very well. And the reason why they do that is the substance would be fully splitting into ions. Every particle that I have of that substance is going to end up creating ions. None of them are going to be staying together. Now, depending on what kind of substance we have, we can sometimes give a different word to that term. For example, breaking apart into ions for ionics is called a dissociation. We can say that the ions fully dissociate from each other. But technically, when we're talking about an acid, acids are kind of somewhere in between being ionic and covalent. They are covalently bonded in their structure, but they do split into ions when they dissolve. And so being kind of in that middle ground, we actually give them their own special term. We say that acids undergo an ionization process, or that they ionize in solution. So technically the two are different. However, you will hear the term dissociation used a lot of times to represent both situations. So don't be shocked to ever see a textbook refer to acids as dissociating. That's commonly seen, but technically acids ionize, not dissociate. The more ions that are made, the stronger of an electrolyte it will be. So the more dissolved ions I have, meaning maybe the higher the concentration of the ions, the better electrolyte conductivity we're going to get out of the deal. These include soluble ionic compounds. So any ionic that does dissolve will be considered a strong electrolyte. Also strong acids. We see we have a very specific list here of these. I will warn you on this sulfuric, the H2SO4, technically just the first hydrogen coming off of it is a strong acid. The second hydrogen coming off is technically a weak acid. However, by that point, you've already created lots of hydrogens, and so therefore it tends to be a very strong electrolyte still. Strong bases are group 1 and 2 hydroxides except Be and Mg. They kind of fit into that ionic category of having a metal with a polyion. And so again, we're going to fully dissociate those and see those ions there. Weak electrolytes somewhat conduct electricity. The reason why is that some of the molecules will split into ions, but some of them will stay together. You notice here we have two categories for this, weak acids and weak bases. Some examples of weak acids are really any acid that's not on this list up here. However, some of our more famous examples include HF, which is hydrofluoric acid, and HC2H3O2, acetic acid, also known more commonly as vinegar. Weak bases are bases that are not hydroxide bases typically. We usually see here what are called amine bases. Amine bases are nitrogen bases. So for example, ammonia, NH3, is what is considered an amine weak base. One last thing I want to mention here about weak electrolytes. You could write the dissolving equations for these, just like I did with the substances up above on the page. However, if I did a dissolving equation for any weak acid or weak base, I would want to use a two-way arrow in their equation. So instead of doing that one-way arrow, I would want to do an arrow maybe where I do a single with two arrows on either side. Or if I want to get really fancy with this, I could do kind of a half arrow one way, a half arrow another way. Some textbooks will just show it like this. They'll put a full arrow one way and a full arrow the other way. So I would want to pick one of these two-way arrows to use in the equation versus the one-way arrows that we saw up above. Non-electrolytes are things that don't make ions in solutions. So obviously if I have an ionic that doesn't dissolve, that is non-soluble, then I wouldn't have an electrolyte solution. Also, all covalent compounds are non-electrolytes. As we talked about up above, if I have a covalent, that's going to stick together in a solution versus creating any kind of ions. And so therefore, it's not going to conduct electricity. All right, let's go ahead and flip to the next page and look at some pictures here of some particle diagrams. And what it wants us to do is to identify each beaker as being a strong or weak electrolyte. And basically the best way to pick this out is to look how many ions I formed in here. This first picture up here, I notice that most of these molecules have no charge at all to them. However, this one has a negative charge, so I have an anion there. And here I have a positive charge, so I have a cation. But hopefully we notice those are the only two ions in that entire beaker. So that means this would be a weak electrolyte here. All right, here's what I want you to do. I want you to take just a moment and see if you can identify the rest of these as being a strong or weak electrolyte. Again, you want to look at, do I have lots of ions or do I only have a couple ions? So take just a moment to do that. All right, did you try those out? Did you put if they were strong or weak? All right, let's see what we put here. This guy, I noticed literally everything in that beaker has some sort of charge to it. So that means I have lots of ions in here, and so this would be a strong electrolyte. Same goes for this one. I have lots of positives, lots of negatives. Everything has a charge, so I have another strong electrolyte. This one here, I'm like, well, this little guy is charged, and this little guy is charged, but nothing else is. So that means this one must be a weak electrolyte. Now, I'll be honest, I actually took some information off of these pictures that they originally had on them. Originally, each of these pictures had it being a strong acid, a strong base, or a weak acid or a weak base. So I actually want to kind of talk through the types that you're seeing here. On this first picture up here with this weak electrolyte, I notice that I have this big kind of molecule here, and that I'm releasing this positive from it. And so what that means is that this is actually a picture of a weak acid. What's happening is that I have my original molecule here that has released this positive ion, which is actually hydrogen. So being that hydrogen ion would make it a weak acid. This specific picture was actually showing acetic acid, which is why the rest of this molecule is so big, because it's trying to show acetate there. All right, this one was specifically a strong base. What it was trying to show is this negative ion here was hydroxide, splitting apart from whatever its cation was, whatever metal it was with. This one here was trying to show a strong acid. So here, the positive was again trying to show hydrogen ion that was being produced. Now this last one over here was kind of an interesting one. This ion here was OH, okay? But you notice here that to get this one, it actually has 1, 2, 3, 4 little atoms on it, whereas the original ones only had 1, 2, 3. What's happening here is that I originally had a weak base of NH3. So this was NH3 that when it interacted with water, one of these stole an H plus from water, which left behind the hydroxide. And what I'm actually forming here with this cation is the ammonium polyatomic ion, NH4 plus 1. All right, let's do one last example today. It says, hey, answer the following questions about hydrofluoric acid. So the first thing I would want to ask myself is it soluble in water? Well, it's an acid, so I'm going to assume that yes, it is soluble in water. Anytime they tell me I have an acid, we assume a state of AQ, which means it is soluble. And then it says, hey, if yes, what kind of dissociation or ionization is experienced? And what that means is, are we doing 100% a full split up into ions, or are we only doing a partial split up? So this is where I would need to think, is hydrofluoric on the strong list or not? Is it strong or weak for an acid? Now, this is where you're going to want to start to really familiarize yourself with this strong acids list. When we get to this spring, I'll really hammer home the importance of memorizing this list. Hydroiodic, hydrobromic, hydrochloric, nitric, sulfuric, chloric, and perchloric. If it's not on that list, it is weak. So since hydrofluoric is not on there, it is only a partial breakup because, again, it is a weak acid. It is not a full split up into ions. So what that means is that this would be considered a weak electrolyte. It does split up into ions, but it only makes a few. A lot of the molecule is staying together. And so we're going to get some ions, but not a lot. So then it asks, hey, what would the dissolving equation for this substance look like? Now, I know we haven't done this for an acid yet, but it basically looks the same way as doing it for an ionic. So I would have my HF, my hydrofluoric acid, and I don't have to put a state to begin with because I don't know what state it would be before I dissolve it in water and make it an acid. So I'm just going to leave it like so. But if this was strong, I would have put a one-way arrow here. With this one being weak, I'm going to go ahead and put a two-way arrow here. So again, you can put your two-way arrow, any of those options I showed you earlier. That choice is up to you. AP would not care which of those arrows you selected. And then I'm going to show that it's split up into ions. So I'm going to have my hydrogen +1 that I'm going to put AQ with. And I'm going to have my fluorine -1 that I put AQ with. That two-way arrow says that, hey, some of this is going to split up, but a lot of it is going to stay together as this original substance. So last but not least here, I want to draw a beaker of what this would look like. Now, here's where we got to kind of be strategic on how many of things we're drawing. We want to show that a little bit of this splits up. And I'll be honest, for weak acids, typically less than 10% of it will actually split apart into ions. So what I'm going to do is I'm going to draw one HF that's split up. So I'm going to draw a hydrogen and a fluorine ion in here. But then I'm going to draw me a whole bunch of HF that has stayed together. So that way I'm showing that, yes, I'm going to get some split up, but a lot of this is going to have stayed together, which is what makes it a weak electrolyte. All right, hopefully we're feeling good about writing dissolving equations, about showing these beaker diagrams. If you have any questions or need any help, please feel free to email me. Bye, guys.